Okay, so today's quiz that we'll start class with. No, I'm kidding. Questions? Questions? Yeah, I didn't get a chance to. Questions about Cal 2? Questions about Cal 2?
Yes.
Oh, okay. Number 8, and you just did a U sub. That's okay. Did it work? Did you take the derivative and it worked? Okay. Yeah. But it would have worked. It probably would have worked with partial fractions also.
How did you do that? How would you do that if you did partial fractions on that one?
You do long division first.
Oh, the powers are the same.
Yeah.
That's right. Okay.
That's it. Probably right after the long division, it's over. I don't think you have to do partial fraction. Well, you wouldn't. Is that good?
Yes.
Okay.
Yeah,
On 29.
I understand like all the way through it all basically.
Mm-hmm.
It's just when you have like the antiderivative of the first part, like the 1/3 natural log of x minus 1 minus the 1/6, and then the second part of it. I don't understand that. Where it went from there.
Where?
This part, because I was trying to watch your video and I just couldn't. I don't know. I got stuck here at the same spot, and then I went to the video and it was just I kind of got confused, and so I just thought I'd ask.
So where do you want me to take it from? Like
From like right here.
Like, you understand how I got that or no?
Yeah, no, I understand this because it's
Just what to do with this right here?
yeah.
Okay. So let me just put it up here and see if this is what you want. You want me to do the integral 2x plus 4?
Yeah, plus 4.
Over
X squared plus x plus 1.
x squared plus x plus 4?
Plus 1.
Plus 1. So if I do this, you'll be happy.
Yeah.
Yes? Okay.
29?
Is that the actual question?
It's part of number 29, I think, right?
Yeah.
So do you want me to do what I did on the video, or do you want me, because I don't remember what I did on the video. I'm just going to look at that as if it's a brand new problem.
Yeah,
Okay.
Yeah.
So if I were looking at that, or if you were looking at that, what would you do? U sub? So you're saying U sub, like make U the bottom and then try and force the top to look like that, the derivative of that? Okay, that's what I would do also, as long as this doesn't factor, which it does not, right? X squared plus x plus 1 doesn't factor, so I agree. Let's do that. So I'm going to let U be x squared plus x plus 1, and du is equal to 2x plus 1 dx, right? So I just need to make the top look like 2x plus 1. So I'm going to add and subtract 1. So I'm going to come in here and I'm going to go, it already has 2x, right? That's why I didn't need to worry about that? You see it now? Yes? So I can stop? Plus 1 minus 1, and then we still had here plus 4, and then over x squared plus x plus 1 dx, like that. If I put these two right here on top of this, then I have U sub. If I put negative 1 plus 4 on the other one, split it apart, then I'll have an integral with just a constant over an irreducible quadratic, which I would complete the square on. Yep. So this would become integral 2x plus 1 over x squared plus x plus 1 dx plus integral, I would have 3 up here, right? 3 x squared plus x plus 1 dx. So this one's done, right? Natural log of absolute value of the denominator is the antiderivative of this. And then over here, complete the square. So do you want me to go complete the square? Y'all want me?
You're good.
You're good. Anyone else want me to keep going?
Sure.
Yeah? Okay, so I'm going to do this one right here. This one's done? Check? Yes, okay. All right, so on the other one, complete the square, I've got to take x squared plus 1. I'm just going to do like scratch work over here. I look at the number in front of x, which is 1. I take half of that, right? All right, that's my first number. I mean, it's just a half. Okay, I don't have to do anything. Then I take that half and I square it. That's 1/4, right? That's another special number. So now I'm going to come in here, I'm going to write x squared plus x.
Minus a fourth.
Other way around. Plus a fourth, minus a fourth. Okay, for completing the square, you always do the plus one. Always the plus first. And the reason why is because when it breaks down to be something squared, right, it's going to be like this one, it's going to be x plus a half, right, squared. When you get that, when you actually square this, that 1/2 and 1/2, that will always be a positive number, even if these were both negative. So that's why it has to be the plus. So this is going to become right here, x squared plus x plus a fourth minus a fourth, and then I had plus 1 there, right? So there's my hidden 0. These three guaranteed to factor to be x plus a half squared, and then these two together become 3/4. Any questions? We're good? So that integral right there is now going to turn into, this one right here is going to turn into the 3 on top, and then x plus a half squared plus, I guess I'll do √3/2 squared. That's just to help you see that this looks a lot like u squared plus a squared, right? So there's a formula, especially if we pull this 3 out. We have a formula for 1/u squared plus a squared. It is arctan. So 1/a arctan of u/a plus c. So we could get, you good from here now? Yeah. This would be, I'll write the answer. It would be 3 times 1/a. A is this, right? It's 1/√3/2 times arctangent of
x or u/a.
what's
So
u
x
for
plus
us?
1/2.
X plus a half over √3/2. And then you can flip it and bring it back through. But now the reason why I went so quickly with this part is because if this is u, if I did a quick little substitution, what would du be? Just 1, right? So let's just say for the sake of argument here, if that's 3, then this problem would have worked out the same, except I would have scaled it out by 1/3, because I would have had to have taken care of that. But I should never have to worry about that on a problem like this. When I complete the square, I should never have to worry about a number other than 1 out here. Why? That's what we actually need to have before we complete the square, right? We had to have a 1 out here anyway. So that should never present itself as a problem. All right. We good? Okay. All right, well, let's see. What's our calendar look like? We've got a test next Thursday. The big test, right? And between now and then, we need to do 5-2, 5-3, 5-4, 6-6. 6-6 is going to take us 2 days, so that's going to be Thursday and Tuesday. All right. We'll talk about it on next Tuesday. We'll talk about whether or not we're going to put all of 6-6 on the test. We might just do, let's just say that officially. Whatever we finish this week will be on next Thursday's test. What we do on Tuesday next week will not be on Thursday's test. That sound good? Okay. That way you have time to do the homework for that. And all right, so today we're covering 3 sections in 1 day, but it's not like, we're going to blow through it and skip over all the, details. We can do all these in 1 day because we've talked a little bit about this. The concept, the principle is pretty clear, all right? It's not like partial fraction decomposition. We just want to know now what those numbers on the ends of the integral meant, right? That's what we want to do. So 5, 5-2, 5-3, and 5-4 deal with what's called the definite integral. and I'm just summarizing all these sections. Now I'm going to put definite integral here. I'm going to put versus the indefinite integral. Which is what we've been doing. I don't know if I've stressed that word to you while we've been doing it, but we've been doing indefinite integrals. An indefinite integral looks like this. Integral, function, dx. Our answer has always been its antiderivative, right? Capital F, remember the relationship between capital F and little f? Okay. The antiderivative of little f is capital F, and then plus c. The reason why we would call this an indefinite integral is because what we're doing is we're finding an answer, which is a function, right? But the plus c means that there's a family of functions. So we don't have a definite answer, do we? We have a function within some family, but we haven't nailed one down. Now, if someone gives us some initial condition, we could actually tell you exactly which function, right? Like if I told you, f of something was, f of 0 was 2. Remember how we did that? Yeah. Okay. So this is why we call this an indefinite integral. Our answer here, this answer, is a function. Now, we compare that to what's called a definite integral, which is the same symbol, but now we're throwing these numbers on here. So we're going to call this a, and we're going to call this b. Here, a and b are numbers. And this is also going to give us some answer, but it's not going to be a function. It's actually going to be a number. So this will be a numerical answer. And so I will write here equals, and I'm going to leave a space intentionally. And I'm put capital F of B minus capital F of A. Now this relationship here, okay, of this integral meaning this, is actually comes from what's called the fundamental theorem of calculus. Fundamental theorem of calculus. There's two versions of the fundamental theorem of calculus. This is commonly referred to as the second version. But this is, whenever we have fundamental theorems in mathematics, when you say fundamental, you mean very important, right? This is a foundational theorem from calculus, that there is a connection between the antiderivative and its derivative, and somehow all we have to do is be able to find this antiderivative and then somehow plug that number, whatever it is, into the antiderivative, plug this number into the antiderivative, and subtract those two numbers. And y'all remember what that represents for us?
The area.
The area. Did we talk about that? Do you remember? No, I didn't? Yeah. I thought we did the Riemann Sums and kind of showed you that, yeah. We voted, right? And I said, do you want to see a little bit of what this really means? And we did look a little. Okay, so I'm going to get rid of the indefinite so I can talk more about the definite. So what this means geometrically is that if you take some function, all right, and you start at a left endpoint of A and end at a right endpoint of B, by finding the antiderivative, okay, so you still, look, we can't get away from the fact that you have to find the antiderivative. But now, once you find it, you're going to plug two numbers into it and subtract them. Once you do that, that number that you get here means what? It means, it represents this area, okay? The area right here would be equal to this right here. And we're not going to prove this because it's a fundamental theorem of calculus. I didn't prove it until I was in a couple of theorem proving courses in mathematics. So we're not going to prove the theorem here, all right? The book does go through some, attempt at proving it, so you can read through it if you want. We're just going to take it on faith that that's what it's going to get us, okay? Now, I do, however, want you to understand the symbols, right? Because I thought that was important. When we were talking about this before, we said what we're going to do is we're going to imagine that there's a rectangle in here. And we even came up with a formula. I remember doing it, right? With you? We came up with a formula for the area of this rectangle. Basically, we said that the width of this rectangle, I'm going to blow that rectangle up. We said that the width of that rectangle, we called that, it was the change in x, delta x. It was the change in x. It was actually, if you go back and look at the formulas, it was b minus a over n. You can go back and look at the lectures if you want. And then the height of this rectangle was the function's value at some point. We could pick the right or the left endpoint, or anywhere in between. Does that ring a bell to you? All right, so then if I wanted the area of this rectangle, it would be this times this. So the area of that rectangle would be f of x times delta x. And then what we did is we said, well, we just want to add them all up, right? We add them up. When you add things in mathematics, we use this symbol, the summation symbol, right? So we add up however many, 100 of them, 1,000 of them. And then what we do is we say, we're going to add up an infinite number of them. So we're actually going to have the width of these rectangles is going to get smaller and smaller, so we get more of them in there. And if you take the limit and you let the number of rectangles go to infinity, right, then you have the true area. And that's where that symbol comes from. So this right here, this symbol, is kind of like this part of it. It's the sum. F of x right here is the height of each of the rectangles. And dx is what we call the differential, is the infinitesimally small width of each rectangle. So each one of these is an area. Do y'all see that? That's an area. And you add up forever, which is this, an infinite number of rectangles. Understand the symbology here? Okay. Is that a word?
Symbolism. Symbolism. Symbology is not a word.
You sure?
Positive.
I'll check on that. You sound too sure. You sound too sure. You're going to bet your life on it?
I would.
Okay. All right.
I wouldn't say
Did you
that.
bet your grade on it?
Would you give me a much better grade? Yes.
All right. Can I look in like an Urban Dictionary?
Symbology is a word. It is
No.
a word. It's a word. It is a word. It's a word.
Okay.
It's a word. It's a study of use or symbol.
All right. Anyway, let's. Okay. So the connection between the picture and this symbol, everyone understand that? That'll become very important later when we're trying to find volumes, is to be able to take a picture and turn it into an integral. And as long as we can come up with a formula, okay, like here, see how we came up with this formula for the area? Then we said just add them up. How do we add things up? Integral, right? So as long as we can come up with a formula later, we'll just turn to the integral at the end, all right? All right, so that's what it means. It represents the area under the curve. And I left a space in here for a reason, and that's because when you're doing definite integrals, what we like to do, is first find the antiderivative, right? Because that's what we've been doing this whole time. So what we like to put here is just capital F of x. Okay, so we're going to say, hey, look, someone wants us to find the area under this function, right, between a and b. All right, first I'm going to find the antiderivative. And then next to it, I'm going to put a bar. I'm going to put b and a. And this just reminds me that once I find the antiderivative, I need to plug b into it, and then I need to plug a into it, and subtract the answers. So this symbol means this. Okay? It's notation. That's all that is. With me? All right. So let's do an example. So as an example, let's find the area under f of x equals 1 over 1 plus x squared on the interval negative 1, 1. So I'm gonna draw a quick picture of this function. I'm gonna graph it, all right? And do it by hand because it shouldn't be too hard to do. What's the value of the function at 0? 1? What's the value of the function at -1? 1/2, right? So at -1, I'm at 1/2. And what's the value of the function at 1? 1/2 again, right? And should we get another one, or do you think that's enough? What do you think it does? Yeah, let's try something else. Let's not go to 2, because 2 is outside of our interval, right? But I mean, if you did do 2, what would it be? 1/5?
Yeah.
So it'd be smaller. So it looks something like it's going down like this over here. It's going down like that. Agreed? As x gets bigger, this ratio gets smaller, doesn't it? Approaches 0. All right, so pick a number that's less than 1, like what, 1/2? So if I do like 1/2 squared, I get a 4th. 1 plus a 4th is 5/4, and then 1 over 5/4 flips, so 4/5. So at 1/2, I'm up here at 4/5, which is pretty close to 1. Then the same thing would happen over here, right? And so what you get is something that looks like this. And what we're trying to do is find the area right there. So because we're trying to find the area under a curve, we're going to use the fundamental theorem of calculus. By the way, this version of the fundamental theorem of calculus is also known as the evaluation theorem. It's the theorem that allows you to evaluate a definite integral. So I'm going to write integral, right? -1 to 1. 1 over 1 plus x squared dx. And I started with one that I thought would be easy. Is that an easy one?
Yes.
Arctan?
Yeah.
Arctan x. That's the antiderivative. But I'm no longer going to put plus c. I'm just going to put a bar. I'm going to put a down here and b up here. I forgot to tell you something earlier. I told you this was a and b, right?
Right.
This is called the lower limit of integration. And this is called the upper limit of integration. Everything else, you should know what it's called. Like this is called the integral sign. This is called the integrand. This is called the differential. Right? We talked about that already. But these two things I never called them anything, so that's what they're called. The lower limit of integration, the upper limit of integration. So you find the antiderivative, great. Forget the c, we can finally throw the c away. And then 1 and -1. And now what I do is I plug in which number first? 1 in first. So I need to do arctangent of 1, and then I say minus arc. What the hell is that? Arctangent of -1. And then you need to know what these are. And you're not going to go get your calculator out. So at what angle is the value of tangent 1? Pi over 4. Pi over 4. Because that's where your x and y coordinates are the same. And so the ratio of the two is 1. Where is arctangent -1? Domain restrictions, yes. Ooh, what are the domain restrictions on the arctan function? Your answer has to be between -pi over 2 and pi over 2. Negative pi over 2, negative pi over 4. That's right. So you have to go back to the, I didn't hear you. If you said that, I didn't hear you. Did you say that?
Yes.
You got to just say it louder if you want credit for it. Don't get mad that I didn't say it was good. Oh, okay. All right. I just didn't hear you. Okay, so this should be negative pi over 4. And those two add up to be pi over 2. So the area is exactly pi over 2.
And we don't have to write any units, right?
It's unitless because we don't know what things are measured in. Now, of course, if this was like in feet, then we would say like square feet. If it was miles, square miles, right? So it'll be a two-dimensional unit because it's area. We all right?
When you say the area is pi over 2, just thinking that it's like from 0 pi to pi over 2, so it's all of the first quadrant?
No, no. It's what I'm saying is that, like, if I give you a rectangle, and I say this is 2 and this is, let's say 3, you know, what's the area of this? 6, right? What's the area of this red? It's pi over 2. See, it accounts for all this weird curvature, and that's pretty awesome. We can get the areas of pretty complicated things. Okay, that all right? All right, let's look at another one. Let's do, I don't know, sine? Let's do sine. Let's find the area underneath the sine curve. And let's look at one period of sine. Sine goes from 0 to 2 pi, right? That's one period of sine. So let's go ahead and find the area. So what's the integral I set up? Integral, lower limit,
0.
upper limit,
2 pi.
okay, integrand, okay, and then we just find the antiderivative. So what's the antiderivative of sine? Negative cosine, x, lower limit, upper limit. Now we're always going to do 2 pi in first, then subtract what we get when we get 0, right? So because things start to get a little more complicated, not necessarily in this problem, a lot of times when I'm doing things, I'll just set up the two pieces first. Like parentheses, here's going to be my capital F when I plug B in. Parentheses here, here's what I'm going to get when I plug in A into capital F. So first I plug in 2 pi. So negative cosine of 2 pi, which cosine of 2 pi is 0. No? No. What is it? 1? That's the same as cosine of 0, which is 1. But then there's a negative. So this is negative 1. Minus, okay, I never did this one. Negative cosine of 0. Cosine of 0 we just said was 1, but then negative. So negative 1 again. And that's just negative 1 plus 1, which is 0. Oh, come on, that can't be right. Yeah, let's take a look at this picture. Well, it's got to have some area, right? If the area is 0, there's sine, right, on one period of sine. If the area is 0, then what's happening here? No.
Negative and positive areas are canceled.
Yeah, we're actually getting somehow this integral, it counts things below the x-axis as negative, even though areas should never be negative, right? So it's counting this as like positive area and this is negative area, and then they're canceling each other out. So that doesn't help me know what the area here is, does it? So what we want to try and do is account for this. So why don't we, instead of doing this, just go to here, integrate to there instead. Whatever that area is, if we double it, then we're going to get the area, right? So this is something we always have to be aware of when it comes to these definite integrals, that it will count things below the x-axis as negative and things above the x-axis as positive. Now, why does it do that? Well, because remember, each rectangle, how wide was each rectangle? Dx, right, or delta x, which is a positive number. But then the height of the rectangle was f of x, wasn't it? And if that height is positive, then we have a positive times a positive. That's going to be a positive number. But if the height of the rectangle comes from the function's value and it's below the x-axis, then that's going to be a negative number, right? And negative times positive will be negative. So it's going to count that area, that rectangle as negative area. And then they cancel each other. Got it? So that's why it's doing it in the formula. All right, so let's do this. Let's change it up. This is the correct answer, okay? If someone asked you to find the area under that from here to here, you would say that because that's the net, right? But what about if they say find the area here to here? Same problem, but from here to pi. So that would change this to pi, this to pi, this to pi. How does that change this answer? Cosine of pi is -1, and then negative, so this becomes +1 now. And this one doesn't change. So your answer would be 2. Yes?
What happens if it goes to like infinity?
What if what goes to
Like
infinity?
0 to infinity? Like the range? Would that still be?
Oh, what if I change the definite integral here and have a limit that goes to infinity? That's 6.6.
Okay.
That's what we start covering on Thursday. If not today, we might get it today. It just depends on how quickly we want to move through this. Questions? Okay, a couple of, let me bring up my notes. I didn't have these opened yet. No, just use it, just leave it as a number. Just a number is fine. What is this? Where is it? Okay, so this is everything. Uh-oh. Whoa. That's not it. 4-7. I've lost it. Is it in my Riemann sums? There we go. Properties. We need to talk about some of the properties of definite integrals. And I'll make this bigger. See if any of those look interesting.